Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool.
Hello everyone. Once again, after an unintentional gap of more than a month, I am PS Chatterjee, and I welcome you to Structural Design Only, a channel with a different vision. Why the gap? Because while developing this sheet, I worked through a complexity of formulas and spent those extra days ensuring they were perfectly customized for you. In this video, we're diving deep into an essential topic for structural engineers, short and long RCC column design, featuring an automated 3D PU, MU, interaction curve. This is the first part of a story-based explanation with complete calculation steps. Before we begin, I want to extend my deepest gratitude to the man whose expertise and inspiration made this video possible. Mr. T. Narayanmurthy. A distinguished civil engineer with a BE and M Tech, Mr. Murthy retired as a chief engineer, civil from the Andhra Pradesh Power Generation Corporation, after decades of exemplary service in thermal, hydel, and renewable energy projects. He generously provided an Excel sheet, similar to the one we are discussing, and gave me his kind permission to share his name and photo. Thank you, sir, for your invaluable contribution to the engineering community. Now, let's get started with the design guide. Title of this slide is Engineer's Goal. Now the question is, what is the engineer's goal? The fundamental goal of a structural engineer when designing a column is to answer a single question: how much load can this column safely carry, in the form of axial load and moments? This capacity is represented by the ultimate axial load, PU, ultimate moment around x-axis, MUX, and ultimate moment around z-axis, MUZ. In a real-world scenario, a column is not just subjected to a straight downward push, PU. It must also resist bending moments acting along both the x-axis, MUX, and the z-axis, MUZ. Therefore, the actual strength of a column is defined by the complex interaction of these three forces. This interaction of PU, MUX, and MUZ forms what is known as the 3D interaction surface. This surface is the map that completely defines the column's load-carrying boundary. Any combination of PU and moments that falls inside this map is safe. Any combination of PU and moments that falls inside this map and close to this boundary is safe and economical. Any combination that falls outside represents failure, and not acceptable. When we design a column, we must ensure that the ultimate factored loads from the structure, consisting of PU, MUX, and MUZ, remain within the boundaries and close to this boundary of this 3D interaction surface for safe and economical design. Because safe and economical design is our main goal. This principle ensures the structural integrity and safety of the compression member. Now let's move to the next slide, for more other explanation. Title of this slide is Maximum Axial Load Capacity MUX equals MUZ equals 0. MUX equals MUZ equals 0 in the title is indicating towards the column is under axial load only. Presently we are not going to consider any moments on the column. And we are also seeing code reference. Before starting the derivation, it is important to understand the code reference. Our calculations are based on the Indian Standard IS 456:2000, specifically Clause 39.3, which deals with compression members. Theoretical capacity. The code defines the theoretical ultimate load carrying capacity of a column under perfectly pure axial compression, called PUZ, as the sum of 0.45 FCK times AC, and 0.75 FY times ASC. This is the absolute maximum strength. Design capacity. However, in actual design, columns must always account for a small, unavoidable bending moment known as minimum eccentricity. Therefore, the maximum practical design load capacity, PU, is slightly reduced and uses the factors 0.40 for concrete and 0.67 for steel. This conservative formula ensures safety against slight imperfections in loading and construction. Focus on the initial formula and its terms. The ultimate axial load capacity, PU, of a short compression member is governed by the combined strength of the concrete and the longitudinal steel reinforcement. The initial formula, based on IS 456, states that PU is equal to the sum of 0.40 FCK times AC, and 0.67 FY times ASC. Now focus on the substitution of AC. Here, AC is the net area of concrete, which is the gross area AG minus the area of steel ASC. By substituting this relationship into the equation, we get a new expression for PU. It equals 0.40 FCK multiplied by the bracket AG minus ASC, plus 0.67 FY times ASC. Now focus on the variable P, known as percentage of steel, and follow the relation of P with AG. AG is nothing but gross area of the concrete. AG equals B times D. We know, here B is the width of the beam in Z direction and D is the depth of the beam in X direction. To standardize the formula, we introduce P, the percentage of steel reinforcement. The area of steel, ASC, can be written as P times AG divided by 100. Now, we divide the entire equation by the gross area AG to get the ultimate stress, PU divided by AG. This yields the expression, 0.40 FCK multiplied by the bracket 1 minus P divided by 100, plus 0.67 Fy multiplied by P divided by 100. Now focus on the final algebraic rearrangement. Finally, we rearrange and combine the terms to get the most commonly presented form of the ultimate stress equation. PU divided by AG equals 0.40 FCK, plus the term P divided by 100 multiplied by the bracket 0.67 Fy minus 0.40 FCK. This final equation allows for easy calculation of the column's ultimate capacity based on the concrete strength FCK, the steel strength Fy, and the steel percentage P. Now let's move to the next slide, for more other explanation. Title of this slide is, Know Your Column with the Stress Block. The previous slides established that our design must account for the ultimate axial load, Pu, and the ultimate moment, Mu. Now, we will look inside the column to understand the internal forces generated by these loads using the stress block concept from the limit state method. When Pu and Mu act on the column, they create internal resistance forces, Cu, the resultant ultimate compressive force, and Tu, the resultant ultimate tensile force in the steel bars. The engineer's goal is to ensure the internal forces balance the external loads. Let's define the key dimensions. D is the column depth. Cc is the clear cover, distance of the external surface of the bars to the external surface of the column. Cover D' is the effective cover to the steel centroid equals to Cc plus half diameter of the bar. The effective depth, D effective, is D minus D'. Now we are going to reveal our stress block. Most critically, say Xu is the depth of the neutral axis of the stress block, which separates the compression zone from the tension zone, developed due to Mu. The resultant compressive force, Cu, acts at a distance Yc, which is 0.42 times Xu, from the extreme compression fiber. The internal lever arm, Z, between the compressive force Tu and the Cg of the stress block, is given by D effective minus Yc. Final equations and the need to analyze the second axis, biaxial bending context. The ultimate tensile force, Tu, in the steel reinforcement is 0.87 times AST times Fy. The compressive force, Cu, is calculated by multiplying the average stress in the concrete by the area of compression. These forces are used to iteratively calculate the depth of the neutral axis, Xu, using the simplified formula Xu equals Cu divided by 0.36 times B times Fck. These are the fundamental equations used for the manual design of column interaction diagrams. Furthermore, when designing a column for moments in both directions, biaxial bending, we must apply these same principles to analyze the second axis. In that analysis, we simply interchange the section dimensions, using D in the formula's width term instead of B. This ensures the section is safe for bending around the Z-axis as well. Now let's move to the next slide, for calculation for strain in concrete and steel. Title of this slide is Calculation for Strain in Concrete and Steel. To determine the exact internal forces in the column, we must first determine the strain developed in the concrete and the steel based on the position of the neutral axis, Xu. The fundamental assumption of the limit state method is that the strain at the concrete extreme fiber, epsilon Cu, reaches its maximum crushing limit of 0.0035. We assume the strain distribution is linear, meaning it varies uniformly from this maximum value down to the neutral axis. The strain developed in the steel reinforcement, epsilon Sc, is found using the geometric principle of similar triangles. The relationship is set up using the extreme concrete strain, epsilon Cu, the depth of the neutral axis, xu, and the effective depth, d effective. This allows us to calculate epsilon Sc at the steel bar level. Once epsilon Sc is calculated, we compare it to the yield strain of steel, epsilon y, which is the yield strength Fy divided by the modulus of elasticity of steel, Es. This comparison is critical to find the actual stress in the steel, Fsc. If the calculated strain, epsilon Sc, is greater than or equal to the yield strain epsilon y, the steel has yielded, and the stress is taken as the ultimate design value, 0.87 times Fy. However, if epsilon Sc is less than the yield strain epsilon y, the steel remains in the elastic range, and the stress is calculated using Hooke's law, Es multiplied by epsilon Sc. This stress value, Fsc, is then used along with the compressive force Cu to determine the column's ultimate capacity for any given neutral axis depth, xu. If this video helped you, please give it a big thumbs up. If you want to support my honest effort, please subscribe. Remember, sharing knowledge means enhancing knowledge, so please share this video with your colleagues. Now let's move to the next slide. Title of this slide is Table H Stress Block Parameters when the neutral axis lies outside the section. In our previous slides, we assumed the neutral axis, xu, fell within the column depth, d. However, when a column carries a very high axial load with a low moment, the entire cross-section may be in compression, meaning the neutral axis lies outside the section. This is when xu is greater than d, or the ratio k, which is xu divided by d is greater than 1. The diagram illustrates this condition. The strain diagram shows the maximum concrete compressive strain of 0.0035 at the highly compressed edge. The strain does not reach zero at the bottom, indicating the entire section is in compression. The stress diagram below it confirms that all parts of the section are subject to compressive stress. Calculating the resultant force and its centroid becomes complex. To simplify this, the SP16 handbook provides Table H. This table gives the simplified expressions for the area of the stress block and the distance of the centroid of the compressive force, Cu, from the highly compressed edge, based on the ratio K. For example, when K equals 1, meaning Xu equals D, the area of the stress block is 0.361 FCK times B, and the centroid distance is 0.416 d. As K increases to 4.0, the area slightly increases, and the centroid distance moves closer to the center of the column, approaching 0.5 d. The note indicates that for constructing the column's interaction diagrams, considering K values up to only about 1.2 is generally sufficient, as most practical designs fall within that range. These tabulated parameters are essential for generating the upper, compression-controlled portion of the Pu versus Mu interaction curve. Now let's move to the next slide. Title of this slide is the dual role of steel, tension and compression bars. Unlike a simple beam where one side is always in tension and the other in compression, a column steel must handle both forces. Now we are seeing, the most popular arrangement of bars are number 1, equal distribution, as shown in the top left diagram. Number 2, along x direction. In this distribution all the bars will be distributed along the x-axis, as shown in the middle left diagram. And number 3, along z direction. In this distribution all the bars will be distributed along the z-axis, as shown in the bottom left diagram. Other than these popular arrangements, we can arrange our bars according to the design needs. Primary consideration should be, this distribution must be closer to the periphery of the column. Because at the extreme edge of the column, both compressive and tensile stress are maximum. Now we are going to see, how we can designate a bar or group of bars as a compression or tension bar. Let's focus on the central diagram. This bar distribution is popularly known as equal distribution. Say we have 12 bars in this array. We have divided our steel bars into rows, R1 to R4, based on their distance from the extreme compression edge. Say center to center distance of the rows is x. This division is critical because the distance of the bar from the compressed edge directly determines its strain and, consequently, its stress. Now we have to calculate the distance of each row from the right-hand side column edge, near to the row R1. The table on the right summarizes these distances. R1 is at D', R2 is at x plus D', and so on. Now we are superimposing the stress block on this column. Say, neutral axis distance of the stress block from the extreme edge of the column is xu. The position of the neutral axis, xu, is the absolute dividing line. Any bar that falls within the depth xu from the compressed edge is a compression bar, marked in the red shaded area. Any bar outside this depth is a tension bar, marked in the gray area. The stress block Cg is where the resultant compressive force, Cu, acts. The condition for determining a bar's status is simple. If the distance from the bar to the neutral axis is positive, meaning it is on the compression side, it is a compression bar. For the specific load case shown here, we see that 4 bars in row R1 are in compression, and 4 bars in row R4 are in tension. For this specific XU shown in the diagram, the total count is 4 compression bars and 8 tension bars. In conclusion, it is vital to remember the dual role. In this load case, bars R1 are compression bars. If the moment reverses, these R1 bars become tension bars, and the R4 bars become compression bars. The column design must ensure the structure is safe for both cases, which is why we distribute the reinforcement to resist forces equally in both directions. Now let's move to the next slide. Title of this slide is, Starting Point of the Long Column Design. Now, we are beginning the RCC column design process, specifically focusing on the criteria for a long column, as defined by the Indian Standard Code, IS 456, 2000. First, we must determine if a column is short or long. To do this, we begin with the unsupported height of the column. This height is the clear distance between the top of the lower support and the bottom of the upper support. After finding the unsupported height, the next critical step is to determine the end conditions, or support conditions, of the column. These conditions define the fixity against rotation and translation. They can be generally grouped as: number 1, fixed end. Number 2, fixed pinned end, or fixed hinged. Number 3, pinned end, or hinged. Number 4, fixed roller end. And finally, number 5, pinned roller end. Along with these end conditions, the frame must be identified as braced or unbraced. This classification is a core concept in structural engineering. It defines how the structure resists lateral forces, like wind, or seismic loads. Based on the end conditions and the frame type, IS 456, 2000, Table 28 provides the recommended values of the effective length factor, K. The values are as follows: for a braced, fixed end condition, K equals 0.65, and for the unbraced condition, K is 1.2. For a braced, fixed pinned end, K equals 0.8, and for the unbraced condition, K is 1.2. For a braced, pinned end, K equals 1.0, and for the unbraced condition, K is 2.0. For a braced, fixed roller end, K equals 1.2, and for the unbraced condition, K is 2.0. And finally, for a braced, pinned roller end, K equals 2.0, and for the unbraced condition, K is also 2.0. The effective height of the column, which can be denoted as LEFF or HEFF, is calculated by multiplying the K factor by the unsupported height. So, the effective height, HEFF, equals K times the unsupported height. Finally, we calculate the slenderness ratio of the column. This ratio, denoted by the Greek letter lambda, is found by dividing the effective height, HEFF, by the least lateral dimension of the column, that is, the minimum value between the depth and the width. This ratio is the slenderness ratio. Now, as per IS 456:2000, if the value of lambda is less than 12, the column is classified as a short column. Otherwise, the column will be classified as a long column. Now let's move to the next slide for more information. The title of this slide is Equivalent Euler's Buckling Load, PCR Equi. In this section, we are going to define the concept of the equivalent Euler's buckling load and its significance in column design. The equivalent Euler's buckling load, PCR Equi, often simply called the Euler's critical load, PCR, is a foundational concept in structural stability. It predicts the maximum theoretical axial compressive load a perfectly straight, long, slender column can withstand before it suddenly buckles or fails due to instability. In our design calculation for a long or slender column, this load is crucial. The stability of the column is directly related to its ratio of factored load to critical load, Pu, divided by PCR. This value is used to determine the moment magnification factor, delta, that we apply to the primary moments, accounting for the P delta, slenderness, effects. Remember, the Euler load represents a failure mode governed entirely by the column stiffness, EI, and geometry, LEFF, not the crushing strength of the concrete or steel. General formula. The general formula for Euler's critical load is PCR equals to pi squared times E times I, all divided by the square of the effective height, HEFF. The key element here is the effective height, HEFF, which is K times the unsupported height, H unsup. The reason we call it equivalent is because Euler's original formula was for an ideal pinned column where K equals 1.0. The K factor, effective height factor, converts our real column with its actual end conditions and frame constraints into an equivalent pinned-ended column that would buckle under the same load. Since we are working with biaxial moments, this general formula is only the starting point. We need to analyze this critical load along both principal axes. Components for biaxial bending. Biaxial components, PCRX and PCRZ. For a rectangular column under biaxial bending, we must calculate the critical load for buckling about both the XX and ZZ axes, as both the stiffness, I, and the end conditions, K, may be different. For buckling about the XX axis, PCRX equals to pi squared times E times IX, all divided by the square of HEFF. For buckling about the ZZ axis, PCRZ equals to pi squared times E times IZ, all divided by the square of HEFF. Note that we use the respective moment of inertia, Ix and Iz, and the respective effective length factors, Kx and Kz, in our formulas. The modulus of elasticity, E, is considered the same for buckling about both axes. Crucially, for a reinforced concrete column, the correct term for E is not the short-term, static modulus of elasticity, EC. Instead, we must use the effective modulus of elasticity, ECEFF, to account for time-dependent effects like creep. We will discuss the calculation of this effective modulus and the effective moment of inertia, IEFF, in the later half of this video. The governing critical load and effective stiffness. The governing PCR equi and effective stiffness. Finally, the design value for the equivalent Euler's buckling load, PCR equi, is the minimum of the two calculated values, as the column will always buckle about its weakest axis first. PCR equi equals the minimum of PCRX and PCRZ. Still, we have not finished the calculation of this PCR equi for a reinforced concrete column. The E and I terms must be substituted with effective flexural rigidity, EEFF, and IEFF, to account for the actual behavior of cracked concrete, creep, and material nonlinearity. Now let's move to the next slides to discuss how we calculate the required IEFF and EEFF. Title of this slide is Modulus of Elasticity of Concrete. We generally denotes modulus of elasticity of concrete by EC. The modulus of elasticity can be viewed in two ways, the static modulus and the effective modulus. First, let us look at the static modulus, EC static. This is the instantaneous stiffness when the load is first applied. For typical calculations, the static modulus is estimated using the formula, EC static, equals 5,000 times the square root of FCK, and FCK is the characteristic compressive strength. Now we move to the effective modulus, ECEFF. This value is used for long-term analysis, as it accounts for the time-dependent deformation of concrete known as creep. The key to calculating the effective modulus is the creep coefficient, phi. This coefficient represents the ratio of the creep strain to the initial elastic strain. The creep coefficient can be categorized into four general levels, corresponding to different loading conditions and time periods: short-term, moderate, long-term, and severe. A value of 0 indicates a short-term load, meaning there is no significant creep effect to consider. As the sustained load period increases, the coefficient moves toward 1 for a moderate creep effect. For long-term sustained loads, the creep coefficient might be around 2. This creep coefficient value is very common to the structural engineer for design a long column in dry climate. In highly demanding situations, or for concrete loaded very early, or very important structure, the creep effect can be severe, with a coefficient as high as 3 or more. Regardless of the creep level, the effective modulus of elasticity is calculated by dividing the static modulus, EC, by 1 plus the creep coefficient, phi. This formula, ECEFF equals EC, divided by 1 plus phi, shows that as the creep coefficient increases, the effective stiffness of the concrete decreases significantly over time. Now let's move to the next slides to discuss how we calculate the required IEFF, or effective moment of inertia of a column section. Title of this slide is, Effective Moment of Inertia of the Column Section, IEFF. We will now calculate the effective moment of inertia along both the XX and ZZ axes. Why do we calculate IEFF? We calculate it for the accurate determination of the column's Euler's buckling load capacity PCR. The effective moment of inertia value, which includes the contribution of the reinforcement bars, is greater than the gross moment of inertia. Using only the gross moment of inertia would lead to an unconservatively high estimate of the critical buckling load. Gross moment of inertia Ig. We already came to know that, the gross moment of inertia of the concrete section along the x-axis is given by Igxx equals d times b to the power 3 divided by 12. Similarly, along the zz axis, it is Igzz equals b times d to the power 3 divided by 12. Here, d is the column dimension parallel to the x-axis, and b is the dimension parallel to the z-axis. Area of each bar AB, the area of a single bar is denoted by a underscore b, which equals pi times the square of d, divided by 4 here, d is the diameter of the bar. Moment of inertia of each bar about its own axis, denoted by IB, we know IB equals pi times d, to the power 4, divided by 64. Again, d is the diameter of the bar. These values are the basic criteria for calculating IEFF. In addition, we must apply the parallel axis theorem for moment of inertia. This theorem states that the moment of inertia of an object about an axis parallel to its centroidal axis is the object's area multiplied by the square of its radius of gyration, r. Here, r is the perpendicular distance of the object's centroid from the reference axis. We are now viewing a typical column cross-section. The dimensions are d in the x direction and b in the z direction. The centroid of the section is at the origin, 0, 0. This section contains 8 reinforcing bars. The bars are arranged in 3 vertical columns. In column 1, we have 3 bars, 1, 2, 3. In column 2, we have 2 bars, 4, 5. In column 3, we have 3 bars, 6, 7, 8. The radius of gyration for column 1 is RZ. For column 2, the radius of gyration is 0, as the z-axis passes through their centroids. For column 3, the radius of gyration is also RZ, but its location is denoted as minus RZ for coordinate purposes. Similarly, the bars are arranged in 3 horizontal rows. For row 1, the radius of gyration is Rx. For row 2, the radius of gyration is 0 because the x-axis passes through their centroids. For row 3, the radius of gyration is minus Rx. Effective moment of inertia along x-axis. Now we analyze the table for the effective moment of inertia along the x-axis, IEFFXX. Row R1, this row contains 3 bars. The total moment of inertia contribution from these bars, based on the parallel axis theorem, is 3 times AB, times Rx, to the power 2. Row R2, this row has 2 bars located on the x-axis, so their radius of gyration is 0, resulting in a bar mi contribution of 0. This is where the gross moment of inertia of the concrete section, Igxx equals d times b to the power 3, divided by 12, is incorporated. Row R3, these 3 bars also contribute 3 times AB, times Rx, to the power 2. The total effective moment of inertia, IEFFXX, is the sum of the total bar MI, IB total and the gross concrete MI, IGXX, plus the moment of inertia of the bars about their own axes IXXB total. Therefore, the total IEFFXX is IB total, or 8 times IB, plus the gross IGXX, plus IXXB total, or 6 times IXXB total. Next, we analyze the similar table for the effective moment of inertia along the ZZ axis, IEFFZZ. Column C1, these 3 bars contribute 3 times AB, times RZ, to the power 2. Column C2, these 2 bars are on the ZZ axis, their radius of gyration is 0. This is where the gross moment of inertia of the concrete section, IGZZ equals B times D to the power 3, divided by 12, is incorporated. Column C3, these 3 bars also contribute 3 times AB, times RZ, to the power 2. The total effective moment of inertia, IEFFZZ, is the sum of the total bar MI, IB total and the gross concrete MI, IGZZ plus the moment of inertia of the bars about their own axes IZB total. Therefore, the total IEFFZZ is IB total, or 8 times IB, plus the gross IGZZ, plus IZZB total, or 6 times IZZB total. This completes the calculation of the effective moment of inertia, IEFF. We will now move to the next slides to discuss the concepts of moment magnification for the column section. Title of this slide is Introduction to Moment Magnification, Step 01. What is moment magnification? Moment magnification is a secondary moment effect where the axial load Pu amplifies the initial bending moment μ, due to the lateral deflection delta. This is also known as the P delta effect. The initial bending moment causes the column to deflect. This deflection then creates an additional moment equal to Pu times delta. The total design moment becomes initial plus additional moments. For design, this magnification factor must be correctly estimated to ensure a safe design. Why and when to adopt moment magnification? We must adopt moment magnification when designing slender columns. A column is slender if the ratio of its effective length LE to its least lateral dimension D is greater than 12. Ignoring the magnified moments would lead to an unconservative estimation of the column's capacity and could result in premature failure due to buckling. The design method must include the effect of slenderness and ensure an adequate reserve of strength. Application as per IS 456 Section 1, Slender versus Short Columns Moment Magnification, also known as the additional moment method, is primarily applicable only to the design of slender columns. Short columns are designed for initial moments or factored moment, MI and minimum eccentricity. For short columns, slenderness effects are negligible, and we do not require moment magnification. Slender columns must be designed by considering the additional moment method, as defined in IS 456, Clause 39.7. Section 2, the additional moment method, IS 456:2000. The IS 456 code directs the designer to adopt the additional moment method for slender members. The key step involves calculating the additional eccentricity EA. The total magnified design moment, MD mag, is calculated as the initial moment MI plus the additional moment MA. The design then proceeds to check if the column can safely resist the factored axial load Pu and the total magnified moment MD mag. Title of this slide is Calculation of Additional Eccentricity EA and Reduction Factor Ka, Step 02. Additional eccentricity, EA. As per IS 456, 2000, this additional eccentricity, EA, is the combination of two formulas, and the first part of the formula is unsupported height of the column H unsup, divided by 500, plus D, divided by 30. Here D is the lateral dimension of the column. And the second part of the formula is squared of effective height of the column, HEFF, divided by 2000 times D. Here, I need to mention that first part of the formula is valid for short column and the whole combination is applicable for long column only. And if this value is less than 20 mm, we have to adopt 20 mm as an additional eccentricity or EA. Additional moment, MA. Now, we are seeing the additional moment MA equals to Pu multiplied by EA. Here Pu is our factored axial load on the column. Moment magnification, MU mag. Now, we are seeing the formula for moment magnification, and the formula is MU mag equals to MU plus Ka time MA. Here, MU mag is our magnified moment, MU is the factored moment, Ka is the factor for moment magnification, Ka, and Ma is our additional moment. Here, other than Ka, we already know the value of other terms. Value of Ka is still unknown to us. Moment magnification factor, Ka. Now, we are seeing the formula for moment magnification factor Ka. Ka equals to Puz minus Pu whole divided by Puz minus Pb, and the value of Ka will be always less than 1. Hence it is also called reduction factor. Here, Puz is the ultimate axial load capacity of the column at zero eccentricity. That means column without any moments. Pb is the equilibrium load. This load is nothing but the axial load that a column will experience when there is moment on the column. Ultimate axial load capacity at zero eccentricity, Puz. Now, it is the time to reveal the formula for Puz. We know as per Indian Standard Code, formula for Puz equals to 0.45 times FCK times AC plus 0.75 times FY times ASC. Here, FCK and Fy are the characteristic strength of the concrete and steel respectively. AC and ASC are the gross area of the concrete and total area of steel provided. Equilibrium load, PB. Next, I am going to discuss on equilibrium load, PB, and the formula is PB equals to CC plus CS minus TS. Here, CC is the compression on the concrete from stress block of the moment on the column. CS is the compression on the steel from stress block. And TS is the tension steel from stress block. Compression in concrete, CC. Next, formula for compression in concrete, due to stress block. And the formula is, CC equals to 0.36 times FCK, times B times XB. Here, XB is the maximum distance of neutral axis from extreme edge of the column. Depth of neutral axis, XB, part 1. Now, the formula for XB. And the formula is, XB equals to 0.0035 times DEFF, divided by 0.0055 plus 0.87 times Fy, by ES. Here, ES is the modulus of elasticity for steel. In this formula, 0.0035 is the maximum allowable strain in the concrete, and we know maximum allowable strain in steel is 0.002. 0.0055 is the sum of this two strain value. Depth of neutral axis, XB, part 2. Now, we are simplifying the formula of XB. We know value of ES is 2 times 10 to the power 5 Newton per square millimeter. Simplified form of XB equals to 700 times DEFF divided by 1100 plus 0.87 by Fy. Now, let's move to the next slide for more formula regarding the calculation of reduction factor Ka. Title of this slide is, Calculation of Reduction Factor Ka, Step 03. Column section and strain diagram. Now, we are seeing a column section along the XY plane. That means, longitudinal section of the column. Say, distribution of the longitudinal bars along two sides, and each row of the column contains 2 bars. At the top of this column section we are also seeing a red dotted triangle. This triangle is our strain distribution diagram. Lateral dimension of the column is D. Effective cover is D prime. Say, we have 4 numbers of column bars, from 1 to 4. Center to center distance of these bars are x. Distance of the neutral axis of this strain diagram from the extreme right edge of the column is xb. So at this point, strain will be 0. And strain at the right edge of the column is 0.0035, which is the maximum allowable strain on concrete. In our previous slide, we came to know how to calculate the value of this distance, xb. Say this distance is such that it covers the second column of bars. Say, distance of first column of bars from the edge of the column is A, and say, distance of second column of bars from the edge of the column is B. Defining distances A and B. Therefore, we can say A equals to D prime. B equals to X plus D prime. Strain on bars. Now, strain on bar, column 1 equals to epsilon 1. Equals to 0.0035 multiplied by xb minus d prime, by xb. Similarly, strain on bar, column 2 equals to epsilon 2. Equals to 0.0035 multiplied by xb minus x plus minus d prime, by xb. Compressive stress on steel. Compressive stress on steel from strain. Say, compressive stress on bar 1 is FSC1, and compressive stress on bar 2 is FSC2. Therefore, FSC1 equals to ES multiplied by epsilon 1, and FSC2 equals to ES multiplied by epsilon 2. Unit is Newton per square millimeter. Compressive stress in steel, effective stress. In this portion, we are going to calculate the excess stress on steel that will be borne by steel, beyond the concrete capacity. Say, effective stress on bar 1 is Fs1. Therefore, Fs1 equals to Fsc1 minus 0.446 multiplied by Fck. Say, effective stress on bar 2 is Fs2. Therefore, Fs2 equals to Fsc2 minus 0.446 multiplied by Fck. Here, 0.446 multiplied by Fck is the maximum stress that can concrete withstand safely, and remaining stress will be borne by the steel within this zone. Total compressive force on steel. Compression in steel bar 1. Say, compressive force on bar 1 is CS1. Then, CS1 equals to Fs1 multiplied by ASC1. Here, ASC1 is the area of compression steel under column 1. Therefore ASC1 equals to N1 multiplied by pi multiplied by d squared, divided by 4. Here N1 is the number of bars in the column 1 and d is the diameter of the bars. Compression in steel bar 2. Similarly, say, compressive force on bar 2 is CS2. Then, CS2 equals to Fs2 multiplied by ASC2. Here, ASC2 is the area of compression steel under column 2. Therefore ASC2 equals to N2 multiplied by pi multiplied by d squared, divided by 4. Here N2 is the number of bars in the column 2 and d is the diameter of the bars. Since the bars under column 3 and 4 are beyond the strain diagram, they will not experience the compression from stress block. Additionally, I have to say that, by the help of this method, we can prepare the 3D, PU, MU, interaction curve for the column. Now, let's move to the next slide for the remaining part of the calculation for reduction factor and moment magnification. Title of this slide is, Calculation of Reduction Factor Ka and Moment Magnification, Step 04. Number of tension bars. First, we will count the number of tension bars. We already know the number of compression bars, which is N1 plus N2. So the rest of the bars will be tension bars. If the total number of bars is N, then the number of tension bars, NST, equals to N minus N1 plus N2. Total area of tension bars. After counting the number of tension bars, we can easily calculate the total area of tension bars. Say it is AST. Then AST equals to NST times pi times squared of D by 4. Here, D is the diameter of the bars. Tension in steel. Now we have to calculate the total tension in steel, denoted as TS. To do that, the formula is TS equals to 0.87 multiplied by Fy multiplied by AST. Here, Fy is the yield strength of the steel. Equilibrium load. Now we know the value of Cc, or compression in concrete, and the value of Cs, or compression in compression steel. And we just calculated the value of Ts, or total tension on the tension bars. The equilibrium load, Pb, is the algebraic sum of these three loads, and finally, Pb equals to Cc plus Cs minus Ts. Reduction coefficient, Ka. Finally, we have calculated all the parameters for the reduction coefficient, Ka. Once again, the formula for Ka equals to Puz minus Pu, whole divided by Puz minus Pb. And the value of Ka must be less than or equal to 1. Moment magnification. Next, we need to calculate the magnified moment for a long or slender column, by the help of this formula, mu mag equals to mu plus Ka multiplied by Ma. Here, mu is the calculated factored moment. Ka is the reduction coefficient for the additional moment, Ma. Final formula for magnified moment. Now we are seeing the reassembled final formula for the magnified moment. And the formula is, mu mag, equals to, mu plus, Puz, minus Pu, whole divided by, Puz, minus Pb, multiplied by Ma. In the case of biaxial moment, we have to repeat this entire process for both axes. In our next episode, we'll dive into building the dynamically interchangeable Excel sheets for the design calculation of short and long RCC columns. Throughout this entire column design series, my main goal is to empower you to build your own Excel sheet. Relying solely on pre-made sheets can limit your understanding. Developing your own truly builds your skills and confidence. If you hit any snags while creating your sheet, remember, I'm here to help you completely free of charge. My focus is always on your learning and skill development. If you'd like to support what I do, here is one simple way: watch my videos in full. Your engagement genuinely helps me improve how I share knowledge with all of you. If this video helped you, please give it a big thumbs up. If you find any poor explanation in this video, please use the dislike button, but always include an explanation in the comments. Sometimes disliking is better than liking, but disliking without context is a verdict without judgment. Remember, sharing knowledge means enhancing knowledge, so please share this video with your colleagues. And if you want to support my honest effort, subscribing to the channel is the best way to do it. Let's grow this community together. Finally, consider a contribution, whatever fits your budget, without any pressure. You'll find the link in the description below. Thank you for your cooperation and support.